It just seems short when I put it in the text.
Oh,
But I did something this time that made it easier putting it into the text. I work in Word. I did screen captures of my charts and stuff, because I hate building charts in LaTeX.
So the only thing I build charts in LaTeX is if you want like a scatter graph or something, where it's really hard to do that. If you just if you could write a Perl script and put all your data in.
Or MATLAB.
Huh?
Or MATLAB.
Yeah.
Yeah.
So.
I don't think I've ever done a chart in LaTeX other than just generate an image, put the image in.
So I have done charts, but it's for like the one I end up always using is like a scatter graph, where you have like just a lot of data. Like, well, I could put this in. I could just write a Perl script that just formats the data, and then you can put it in a separate file and just have LaTeX, and it just grabs it out for you.
Okay.
Yeah.
Make an image.
Yeah.
Yeah, I usually have it in Python anyway, and so it's just okay. Matplotlib, done.
Everything else I do exactly, it's just screenshot.
yep,
Yeah.
Load in.
Yep.
yeah, that's.
And then
what
tell
we did too.
LaTeX, no, really, I want it here. No, really, I want it here.
Exactly.
It's like all the stuff.
Asterisk,
philosophy,
asterisk,
like,
asterisk, asterisk, come on.
And it does it for you because it knows better than you.
Uh-huh.
So then you're like, no, you don't know better than you right now. It's a terrible place to put it.
How long did the report tasking be for like visualizing that?
For
Screw the escape
for-
characters.
For the project, the report?
I could not
For
get it
the-
to take a
like the
slash.
programming project?
No, it's just a slash. It's just escape character slash. Okay, I'll put another
Yeah,
slash.
just take screenshots,
No,
no,
it's
just
not
the
a-
content.
Yeah,
return.
Totally.
Slash,
Just
slash,
make sure
no,
it's
elementary.
there.
Oh, yeah, for the project, technical reports, is it just like showing us like how we did it? Or just like, I've seen a lot of like, you know,
So-
people like to have like a readme.
No, the report is for the project, for the programming project.
Okay.
Is not a paper. It is, I did X, Y, and Z. This is how it works. This is what was hard. This is what was easy, and you know.
Okay.
How you compile it would probably be nice for me.
Sure.
So I noticed on the assignment for that it says like make sure it runs on the Linux system in the data center.
Yeah.
Do you care, or is it like, okay, you type make if you have client installed?
Yeah. Type make would be great. I'm gonna test them in VMware, so it's just easier for me to just
Yeah.
have VMs that already network together. It's way easier than dealing with the school. But not everybody has VMware. And then if I say, hey, do it in VMware, then I'll get all these questions like, I don't know how to use VMware. I'm like,
Do you think we still have some people that didn't know how to use VMware?
yeah, I think so.
Yeah,
Yeah?
Yeah.
yeah.
Okay. Sorry.
It's really easy to not know how to use something.
It's just, you know, simple idea, just like having OS that you didn't have and installed in VirtualBox or whatever.
Yeah, VirtualBox, VMware, or whatever. I'm just taking your code and putting it on two VMs that are already networked together.
Yeah.
Run it, bang.
But as I said, like I implemented in the same one, but just like have two directory, and I can see that the file transfer to the other one. It's not real networking, but it's, you know,
What are you doing?
it's communicated through the socket, so
Uh-huh.
it's transferred through the socket. But even though they are both implemented in the same host.
As long as it goes through the socket. So
Yep.
if you wanna like push it to 127.0.0.1 and
Yep.
pull it back down, different port, that's fine.
Okay. Okay.
Yep.
Okay.
So you didn't have
But
to
so
do-
long as you're calling socket and actually using it. So
Yeah.
gotta qualify that.
Yeah.
You're like, I called socket.
TP it over.
But it's remarked out.
That's right. Or you just call it and close it and do something
Yeah.
else.
Must be
Oh, wait a minute, this is
Just put it on Dropbox.
research programming, you call it and don't close it.
It's part of my security.
It's
It's-
inside your closed socket, shell out to CP. You know, if you're running it on VMware, there's a network conditioner you can use to inject packet loss, I think, so you could legit test it
Legit test it and see if it works.
instead of relying on our own
That's right, because
janky packet
so you,
dropper.
you think of different ways that you can game it, right? You're like, oh, well, I'm gonna inject I'm gonna inject errors at this very particular algorithm, so I can correct errors at this very particular algorithm on the other side.
Flip and flop.
We're still in chapter 6, right? The transport layer?
It's transport, it's congestion, yeah.
Oh, okay.
We're just gonna go through congestion and then we're gonna go to miscellaneous topics after. Mostly security, because like half you guys are security makers. All right. It is really cold here today.
It's
That
really
or
cold
in
it's
general.
6 or possibly both. All right. So we introduced what congestion was, and congestion is when the network itself gets clogged. So it's not. We talked about developing a sliding window if your clients are their buffer is filling up, right? But the question is, how do you detect that there's congestion somewhere in the middle of the network? So it's not the other client on the other side. So there's congestion in the middle of the network, and their buffers are filling up, right? So how do you do that? So before we get in there, let's just talk a little bit about kind of what the goal would be to take care of congestion in the network. So we always have a goal of filling up the network, right? And that goal of filling up the network is efficiency. So let's say, for argument's sake, that all the connections that are going in and going out are one. So if all the connections are one, how do we do, and we gotta divide this up into some portion of one for the incoming connections. How do we do that efficiently? And then on top of that, how do we do it fairly? Because we could always do the HBO Go thing, right? And like, Sunday, we're just cutting HBO Go off, right? That's not necessarily fair, but it could be efficient. So what do we want, how do we actually achieve this? So this in total right here is 1, and this is 1, like every connection is 1, right?
So it's that 1 plus 1.
Huh?
2 ones, right?
So no. So we have this thing is capable of 1 unit. We'll just call it 1 unit. And we want to transfer data from one side to the other. So this might look more appropriate. Let's put it this way. Right, because there'll be a connection between the routers. Looks better that way. So the cost of every route is 1, right? But we have 3 connections, right? So in order to do that here, you know, we divide it up into thirds. Right? If we divide it up into here, what would it be?
2.
Oh, this is, yeah, so it's half, this is 1, right? 1, 1, 1. And 1, obviously. So if we, the problem now is, okay, well, now we have a bandwidth that's half here, it's a third here. If B is going through and heading northeast to this one, right, now we have 1, right? So we have to design an algorithm that we can divide all this stuff up. And we have to be able to do that in a somewhat efficient manner, and again, we have to be able to do that in a distributed mode, right? There's no massive architecture that says, hey, this is what we're doing. Right, so just intuitively, how would you divide this network up? Oh, by the way, now this is actually got another one because we went both, right? So this is half two.
Is there a delay in the network?
Huh?
Is there a delay in the network?
So there is a delay, right? And that's how we determine the flow, is the delay from the bandwidth delay product. Right, but now there's other delays in the network. So let's consider a simpler network. A, B, and C. So A wants to talk to B, right? So these are routers, right? And there's hosts that go in. So A talks to B. Now A also wants to talk to C, and then B wants to talk to C. Right, it's just a simpler version of the same thing. We're, instead of dividing up paths, we're just going across the same path. Right, all have a cost of 1 again. So this is 1/2 and 1/2, right? And this is 1/2 as well.
It'll be 1/2
One
and 1/2
third?
as well, right?
What about A to C?
So A to C is this here. A to C is 1/2, right?
Okay.
A to B is 1/2, and B to C is 1/2. So we have a dilemma here. Our network capacity is 1 from A to B and 1 from B to C, right? But the network capacity as a whole is actually 2, right? And we're only filling it up with 3 halves versus 4 halves, which is 2, right? So there's this dilemma on how do we take maximum efficiency of the bandwidth that we have, and everybody competing for that, and still make it fair, right? So the HBO Go method, right, is get rid of that, and now we have a maximum efficiency, because this is 1 and 1 now, and we're filling up our network, right? So we need some kind of balance.
Is that when you get the maximum efficiency load over the delay?
So efficiency always is in contention with fairness, always.
Okay.
So back to this network, right? Intuitively, well, we get a third here, right? But when we come out of here, now we have a third of the traffic going over a half length, right? And we've got a third of the traffic going over a half length. And this third is going over a full length, right? So this one is operating at 33%. And then this one is what? Be 16.66
Yeah.
minus 100, whatever. So 80, just say 84%. Right? So we have an efficiency problem. Now, of course, we're sending packets, right? So these aren't like steady beams of electricity that are moving across, right? We're sending signals, and we're sending those signals in discrete chunks. So we could also look for a way to use that property that we are sending packets across the network to balance things out. And this is a very static network, right? So it doesn't probably operate like this all the time. Sometimes, right, one computer quits transmitting, and then we're at a half again. Well, half is very convenient for us, right? So we fill this up. So, but we need an algorithm to be able to determine that. And we're going to use the same property of Windows that we had before to try to balance this out. But in order to do that, we need signaling. What signaling do we naturally have in the network to start with? We used it to determine our windows already. So remember, if you send a packet across the network, right, eventually you'll get an ACK on the way back, right? And if you get the ACK on the way back, you can determine the bandwidth delay, right? Overall, the bandwidth delay. Now also think, if you send a packet over the network, let's say you just stuff a bunch of packets on the network right quick, right? Do the ACKs come back at the same pace? No, they do not. So now consider that you have super fast connection here, right? Very simple network. This is slow, right? And we have a super fast connection over here, both tunnels. Now let's stuff a bunch of things on this network. Let's stuff 5 packets back to back on this network. What happens when it hits here?
They get transmitted
So they can't go out as fast, right? Because it's a slower connection. So there's a buffer in this thing, and it fills up, right, as the first one goes across. And then when that one gets put on the network, right, it moves over, and then you have like this, where they were very close together, and now they're very slow. What happens when it gets here? Does it change? No, no. They all come out the same. Doesn't magically get closer together, right? Yeah, some time travel involved, right? So it doesn't magically get close together. And then, so this thing receives a packet, it sends an ACK, right? And that ACK is gapped here. It's not gapped here. So shove a bunch of packets on the network, right? Then the ACKs come back and they're spaced apart. So we do have a signal across the network to tell us how fast packets can arrive.
Question, so when they're separated in the middle, when it comes out at the end, does it still separate, would the speed differ? Would it go out?
No, so if this connection is fast, this one's slow, and this one's fast, we can put them all on the line really fast here, right? Because we have a fast connection. Then they go across this line slow, and even though this line is still fast, right, they're only arriving at a certain pace. So basically, there's a buffer in this thing that's not getting filled. right? It just goes to the first level and is shot out again. Now, also consider what happens when the network gets congested.
It's gonna be slower.
Huh? It's going to be slower. Can we measure that still? Yes, we can measure that still. Right? So we have the natural bandwidth across the network, and we get our pacing out of the slowest bandwidth. But as we get congested, then we're filling up buffers, and so it gets even slower still. And eventually you'll get a packet loss. Packet loss is another signal that you can use that things aren't going quite correctly.
So one question, what protocol are we using in this case? Is it just?
So we're just working, this is just signaling, right? So like, let's say you had a network, no protocol or whatever, but you can make a packet, right? And so you build this rudimentary version of TCP. None of the stuff that we're talking about today is in it, right? And if everything went correctly, you could shove a bunch of packets on the network and you can measure the pace of the network on the other side. So there's no congestion, there's no packet loss or anything yet, right? But we could do that, and we could do that with very simple code, right? So long as the network layer exists, right? Make it TCP basic header to go to a port and then shove it on there as fast as possible and see what happens. And you get the measurement on the other side. So, we got a measurement of pace on the other side. We can also measure congestion by a change in pace. And we can or at least maybe infer congestion. Aren't there other things that could happen that cause packet loss other than congestion? Right? It could just be an error. But there are signals. The point is there are signals on the network that we can use without building anything in the routers themselves. I'm gonna show you that can be done, and then I'm gonna immediately tell you it would be better if we put it in the routers, which we have. Right? So, the question now is, from a mathematics standpoint, how do we find where our optimal level is? So there are signals that exist that we can measure, right? How do we find what that optimal pace is?
Is that when the furnace line attaches with the efficiency line, so you get the main midpoint for the optimal
Correct.
point?
Yeah, exactly. That's exactly what it is. Right? So we have a fairness line. Fairness is everything is equal. Let's just say our connection is 1 again. Right? What's the efficiency? Efficiency is everything added together equals 1. So then what becomes this? What is everything on this side of the line? Equals more than 1, right?
Yeah.
So that's congestion. Can we get past 1? We can,
It's just not-
momentarily, right? Because we can fill up the buffers in all the routers. So we can actually achieve past 1 momentarily, but you can't maintain it there. This is fairness, right? Fairness is everybody gets equal, right? So then this right here is optimal. The question is, how do you find that point? So it's easy, you got 2, right? And all the line speeds are the same. Oh, it's just half, right? Or if you had 10 and all the line speeds were the same, oh, it's just a 10th. That's not the case. All the lines aren't the same, right? You're going over 10 different lengths, right? Some of them are fast, some of them are slow. So the question is, how does a host independently, or how does anybody, let's just start with the math part. How does anybody find where this point is.
So, we can calculate the slope of the junction of the two lines.
So this slope is 45. So is this one. But that is in the very simple case of one, right? If we had different ones, it would be, like, let's say that this one has 2 or whatever.
If we know like the functions for those curves, we just have it equal to each other.
Yeah, but now you kind of got to measure the whole network again.
So I'm thinking more from an application perspective, won't it know buffer sizes and speeds of its clients based on when it initially sets up windowing with each client?
So it knows its own. The problem is it knows nobody else's. This is a distributed system, right? So it knows its own and it can measure its own, right? But it doesn't know anybody else's parameters. It doesn't know anybody else's connections. It can only measure your own.
Just start sending packets out.
It's not a bad idea. What if we started sending packets out, right? What if we, if we start sending packets out, and that happens to, in our theoretical graph, ends up here. Well, we haven't made the network better yet, right? So what do?
Send another packet.
We send out more packets, right? And then we end up here. And then more packets, right? We end up here. Then we detect loss,
Oh, so that's how you measure there, is because you detect loss.
right?
Dropped.
Because we get a drop packet,
Okay.
right? So what do we do now?
Taking the average maybe?
Huh?
Taking the average between
So-
before getting lost and.
What we do is, so we were adding to get here. And then we multiply by a fraction to move back.
So it's just throttling, basically.
So you add, right? If you subtracted, then you're not moving into fairness, right? Because there's another guy that's competing for you to do. The idea is, how do we get close to here? This is fairness. This is where we want to be, right? So if we add, we move this direction. If we multiply by a fraction or divide, where do we move? We move towards the origin, right? So then we drop back, and we're here, and we're here, and we're here, and then we move towards the origin, right? And then we're here, then we're here, then we're here, and you'll recognize that eventually we'll get here, because you always move towards the origin. So if you were down here, right, you get better.
So you just do it a whole bunch of times and then assume we're on the line now.
Yeah. Yeah, and you continually do that every time you receive a signal, whatever that signal is, that hey, the network is full. You throttle back by multiplying by a fraction, right? So this is adaptive increase, multiplicative decrease, right? So we add additive increase to move forward, send more packets on the network. When we hit too much, we multiply, which is really divide out a portion. We multiply by some kind of percentage.
It's like when it stops changing, you converged.
And when we converged, right? And then when somebody gets on the network, extra person gets on the network, right? It changes your fairness point, and everybody converges to that point. When somebody gets off the network, you get more bandwidth, right? It changes your fairness point, and everybody converges to that fairness point.
So you're like continually doing this.
You continually do it. Every time I get a signal that I hit congestion, that something is full, I adapt. But this is all great in theory. We haven't actually talked about how you get there yet. But this is the math part, right? This is what we want to achieve. Now the question is implementation. How do you actually achieve that? Oh, And then what would your throughput line look like? Huh?
Yeah, like a zigzag.
Yeah, looks like this, right? With congestion. Right? Every time we hit over the congestion point, start losing stuff, we just drop back down. And we start creeping back up, drop back down.
What did you say that line was called again?
Huh?
That throughput line?
So this is actually the throughput, right? But throughput, not good put, right? This is throughput, right? Because our good put looks something like this, right?
Smoother than.
It's because all this stuff over here, there's lost packets up here, so then you have to retransmit, right? So, this was actually not thought of in the early days of the internet. So in the early days of the internet, and I think it is like 1986, the entire internet collapsed, quit working for all intents and purposes. And they didn't know why. There was lots of packets going across the network, right? But there was no good put going across the network. Because nobody had thought, hey, how do we do congestion control? Right? We built this network and we can determine things, locally. Nobody thought through the idea of how do we actually, whatever. It's the same old adage, right? If you make it bigger, we'll just fill it up. So, what's the two things that a garage and a hard disk have common? They're either new or full, right? And so the internet was the same way. The internet was the same way. We filled it up in 1986 and it quit working. So, a guy named Jacobson, which is not totally important, but he was a smart guy and contributed a lot to networking, came up with the idea, hey, we have signals on the internet, those signals that we just talked about. And if we have those signals on the internet and we all play fairly, remember this is still a playing fair game. So the only thing malicious is naive maliciousness, right? So if everybody plays fairly, then we have these signals on the internet. Why don't we try to use those signals to throttle back as we approach congestion? And one of the first ideas on that was using that ACK clock. That signal as you go across the network, you can clock how fast your ACKs are coming back. And if your ACKs are coming back at a rate, you can throttle back your push rate to match your acknowledgement rate. Right? It's not a perfect solution, right? But we could use that. One of the things that if you do that, it smooths out all your network traffic. Right? So you're not filling the buffers close to you or somewhere in the middle, right, when you hit that first link that's slower than what you're uploading on. And it also, if you got that ACK clock, so remember we had a buffer window to determine the number of frames that we're going to do. If we have an ACK clock, we can also determine a window of the number of frames that we're sending out, or segments that we're sending out. Actually, no, it would be packets, because it's at the network layer. We can measure the number of packets by the number of acts coming back. And if we have that number of acts coming back, then we can determine a second window. So the framing window was the first one to fill up the network, right? The second window is a congestion window of the number of packets that we think that we can send on this network. And that's going to change over time as your act clocks changes. The problem is if you're broadcasting across the internet, there's quite a delay from the time, it doesn't seem like a lot, but from a computer standpoint is gigantic. From the time you send out a packet to the time you get your acknowledgement. So what are some other ways? So let's just put it in a loop here. We're transmitting A to B, right? This is our acknowledgement window. The timeout for this acknowledgement window, let's say the acknowledgement window is here. Your timeout actually looks like something like that. There's a big gap. It's much bigger than the actual acknowledgement window. And you have to have that because sometimes it will be slow. So this is, if you were doing stop and wait, this is the problem that you're in. But we're not doing stop and wait. We're sending out many, many frames. So I told you on Wednesday that when you send out an acknowledgement, TCP can send out the cumulative acknowledgement, where I am at now. It can also send out 3 separate ranges for immediate replies. So, like, let's say we have a cumulative of 100. So every sequence number up to 100 is I have, right? And then and we're just doing 100 blocks, right? And then I receive like a 300 to 400 next, right? So 100 the first time, and then 100, 300, 400 next time, right? And then 100, 300, 400, 400, 500 this time, right? Instead of drawing it all out, 3 separate packets, right? So I'm getting, these are basically duplicates, right? My cumulative is not going up. If I receive this 200 packet here, right, I would immediately jump up to 500. But I'm not, right? So we could use this as a signal to determine, hey, I may have lost a packet, and we can determine this way before our timeout has elapsed. Way before our timeout has elapsed. So what TCP, the early versions of TCP did, was you would receive this 100, right? And then on this one here, right, this would be your first duplicate. And then this one here would be your second duplicate. And then let's say you receive 500, 600, that'd be your third duplicate. It immediately resends. And so this is the out-of-sequence transmission that TCP does that we were talking about on Wednesday, but it's also another signal. It's a signal that we probably have lost a packet. Have we definitely lost it? I don't know. But there's a good chance that we have. Right? And we know this way before the timeout arrives. So what do? We throttle back. We slow down. So the next question is, how do you slow down? How do you speed up? How do you slow down?
Congestion.
Huh?
Congestion. You slow down.
Well, so what we do is we're changing our congestion window, right? We make our congestion window smaller to slow it down, right? But the question is, how do you turn it on? How much you do that? So, if we started from one packet, like let's say we're in our timeline window, A to B, A is gonna talk to B, and B is gonna acknowledge, right? Nothing complicated, just one-way communication, right? So A talks to B, B acknowledges, right? So now we stuff, before we, just assume we stuffed a lot of packets so we can at least get our ACK window. But it's gonna make the graph very complicated. So let's just stick with this, right? So we can increment, right? So we got a good acknowledgement, right? And so we want to do that additive increment forward. So we can send, this time, send 2 packets. They won't arrive at the same time because if you send 2 packets, then there is some delay, right? And then we get acknowledgements for these things. And then on the second acknowledgement, we know that, hey, our 2 packets made it. We send 3 packets. Notice we only do it on the second one, right? Or the last one, right? So this one we get 3 acknowledgements, and then on the third acknowledgement we know that we made it, right? We send 4. The problem is if you're doing this, there are likely hundreds, maybe thousands of packets on the network. So this is going to ramp up very slow. Right, so if we had a graph where this is our capacity that we don't know, because if we knew it, we could just go to that, right? So this is our shared capacity, and we don't know it because other people are on the network, right? This thing's like, takes a long time to get there. So what else could we do?
Double the number of packets or something?
Huh?
Like double the number of packets each time.
Just go up by 1,000 and then drop down by half.
So the simple way, right? Right, computers, that sounds like a programmer right there. Bam! Right?
Hit the ceiling.
Hit the ceiling, right? So hit the ceiling. The problem is if you hit the ceiling immediately, then you don't know where you were before the line, right? So if you just try to jump up, right, it's really hard on the network because you get this really big giant burst of packets, and likely you don't know exactly where you were before here, right? You just filled up the network, right? So then you could try to guess here somewhere, right? But then it becomes a computing game, and I'll tell you in implementations they do guess some of that. The other way is double your packets. So this was additive, right? Which is what we're trying to achieve, is additive and multiplicative reductions, right? But if we started out multiplying, we could quickly find at least halfway where we need to be. So we get our ACK, right? And as before, we send out 2, right? And then they come back. And then we send out 1 for each of those. Right? So 1, 2, 4, 8, 16. And of course that line is exponential, looks like this. And then when we hit here, we know about where that is. It's half of where it was before we hit it, right? So then, when we find that halfway point, then we start adding. And we reach that place very quickly. In real implementations, they do kind of all 3 of those things. Need a different color. So in a real implementation, they'll have like this place where they're pretty sure that they can get to, right? Followed by an exponential curve and a drop back, right? That determines there, and then they get there.
So if we're multiplying the number of packets,
Yeah, so if we get a good set of acknowledgements, for every acknowledgement, we send out 2 more packets.
But then we have a function to do that on the host side.
Yes, yes, this is all on the host side.
But
This is all host dependent.
okay, so, but would that not be slower in terms of the processing overhead as compared to when we just have to hard the packets? I'm talking in terms of the functionality.
So it rises in real implementations, we pick a starting point that's way higher than 0. Then we increase exponentially up to here. It's actually not, because you're already at a starting point. The exponential curve looks really steep from there. And then we drop back to half of where we were the last time, and then we take a additive on the way up. And remember, additive doesn't necessarily mean that you're adding 1,
Okay.
right? So, let's say this was 10,000, right? You might want to start adding at like 1,000, right? But it's still linear. It's just you're changing the steepness of the line. The main point is there's a way to take an exponential line to find that place quickly, right? And then take a linear approach to finding this. So it doesn't have to be 1 to 1, right? It could be 1 to 1,000 for every increment, and you just change the steepness of the line. Because up here in a real network, you're dealing with very big numbers. So you're not gonna drop, from 1,000 packets to 500 packets in an increment by 1, right? So ironically, it's the weirdest name ever. That exponential part right here is called slow start. And it's slow because it's not this, let's start up here, right? It's slow because there is a slope at the bottom that's not near straight up. And so this is slow start to ramp up, and dealing with the acknowledgements rather than waiting for a timeout. So looking at the acknowledgements and looking for out of order acknowledgements, or they're technically duplicate acknowledgements, but there's a gap between the cumulative acknowledgement and the secondary or ranges, right? So if there's a gap, then they can infer that you've lost a packet. That's really important, because if you wait the other way, if you wait for the timeout, what is our ACK clock?
Double.
Our ACK clock is 0. We've exhausted our ACK clock. So if we wait for the timeout, then we are no longer receiving ACKs. And so we no longer have an accurate to-date measurement of our ACK clock. So what do we gotta do? We have to start over. We no longer have a good ACK clock. So we have to start over from scratch. The early implementations of TCP did that thing. And then they added the ranges in there, because you could, not only could you have fast recovery for this, right, but you can also have fast retransmits for filling in gaps on the other side. And it was what, the fast retransmits were already coming to be, and that was another signal that we could use to improve TCP. in this version of TCP, I mean, we missed that kind of research by only like 10 years. So the next best way is, hey, maybe on new routers, we'll send a signal directly from the router to say, give me full, right? Because then that only improves the network. The faster you get the signal, and the more, so when you're dealing with acknowledgements, there's a possibility that you just had something go wrong on the network. There could be one link got really congested and there was a different route taken because of congestion control locally on the router, right? Which changes your ACK clock, right? So there are things that are not exactly great about using ACKs for your timing, right? There could be better, and better would be, hey, instead of looking at round trip time, which is a long time, there is some fuzzy logic in on whether this actually is because the network is congested. Let's just have the router tell me. If the router can tell me, then it can do better. And that is called explicit congestion notification, which we will talk about a little bit. So I'm going to pick out a couple problems to do on Wednesday so that we can go through them. Some of this stuff nothing is as bad as physical layer, right? But some of this part is slightly more difficult than like the network layer and routing, at least the simple parts of that. So I'll pick out a couple problems. I'll see if I can get those posted tonight. We'll run through those problems. We only have one little tiny section on explicit notification. We'll cover that and then we'll do the problems. That'll give a good segue to the homework assignment, which will wrap up everything to TCP. And then we will cover the miscellaneous topics, namely network security. Because all the stuff that we've done so far has all been everybody's playing fair, right? What are some of the unfair things you can do in what we've talked about so far, even today?
Request an act for something you didn't send.
Huh?
Request an act for something you didn't send.
Yeah. Or you could just fill the packet full of network, or fill the network full of packets.
Yes.
And never stop.
Right?
Yeah.
And you're like, and just totally ignore your ACK window altogether, right? Just keep stuffing them on the network, right?
Throwing them out of broadcast address, they just keep.
Correct, right? There's other neat things you can do, is you can send a packet to a different computer with, so if you want to attack B and you don't want to know that you're A, you send a packet to C, right, that is malformed, and have it reply to, right, and so you can do ACK flooding, and you can do, there's just a number of things that you can do from a malicious standpoint, because everything that we've done so far talks about, hey, we want a distributed algorithm where everybody's playing fair. So the next question in security is, what if people aren't playing fair, right? What if they're trying to, what if they're trying to consume more bandwidth than they've been allocated to, they're simply trying to deny you bandwidth, or a number of different things. So we will jump into that. That's all I got today.
As long as the presentation, you want to have about 8 minutes, is it?
About 8 minutes, yes.
Always 15,
Oh, 8
right?
minutes for our presentations?
Yeah, so, yeah.
Oh, man.
This ain't your PhD, Steve.